I'm Sidhant, and this session is about week, I think week 5, I'm not sure, but it's basically the mathematical topics of comparative programming. And yeah, so everyone can see the Sublime text, I assume. Somebody raised their hand. You don't need to actually raise your hand. Like, just ask your questions on the chat if you have any, or just unmute yourself and say out your question loud. So hope I'm clear and audible. In case in between I'm not audible, just again message on the chat. So today's agenda is basically these 4 to 5 things. First is so like a lot of questions of number theory, at least up till the intermediate level, I would say, or mathematics, involve. Okay, so someone is asking which contest is this. Let me see. Okay, it's contest 5. Yeah, Navjot, it's contest 5. So somebody, so a lot of problems up till the intermediate level involving number theory have this generic method which can be used, or like at least it's a way of thinking that's like helpful, which is to always think of like the numbers in terms of their prime factorization. So don't think of numbers as themselves, but always try to think of them in terms of their prime factorization. The idea is that, let's say you're given an array A, which is like, let's say something like 100, 30, 45, 67, blah, 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 some question. Now, don't think of the array as such. Like, obviously, the array will be different for different inputs, but don't think of the array as numbers. Instead, think of the array as the prime factorization of each thing. So something of this sort. And 3 into 3 into 5 and dot, dot, dot. Basically, think of each element as its prime factorization. The benefits are a lot when you start thinking about mathematics for comparative programming, at least like this. Okay, let's go through some quick examples. What if I have an array of integers and I have to find the LCM of those integers? LCM of an array of integers. Does anyone have any ideas? How should we do this? Again, one method could be, so some people might have heard about this thing that basically LCM is equal to product, like LCM of A times B is equal to A times B divided by GCD of A of A and B. And you can extend this to multiple things. You can extend it to 3 elements also. You can just say LCM of this thing with C and then dot dot dot. Blah, just expand it. But it gets ugly pretty quickly. And one of the issues you'll be facing is that LCM actually does come out to be quite big. Like, think about this. If I have numbers, if I'm taking LCM of all the prime numbers, then the LCM will actually be the product of all the prime numbers, right? So the LCM actually grows pretty fast. Let's say you were asked the LCM, or you were asked like LCM module or something. Yeah, then Jacob answered it correctly, that just take the least power. So the idea is that if you have a lot of numbers, let's say A1, A2, dot, dot, dot. Okay. So now I'll switch to my iPad to show this question, like how to do LCMs and HCFs, GCDs. Another question which like you can just go through right now, at least the question, and like we solve it on the whiteboard so that it's easier to write. The question is, given a number, you have to quickly identify if it's square free or not. That is when is a number square free? A number is square free if none of its factors is a square number. Example, say, I don't know, let me think, 50 is not square free. Why? Because 25 is a factor of 50 and 25 is a square. Okay, so basically a number is square free if all of its factors are not square numbers. Basically, none of its factors should be a square number. Another example could be, I don't know, 30. It probably is square free. Because like just iterate over all the factors of 30, 1, 2, 3, blah, 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 5, 10, 15, 30, and none of them are squares. So factors which are not 1, a square free number is a number such that the factors are is a number such that the factors are a perfect square. No, I'm saying that the factors are not a perfect square. I mean, that's why it's free of the squares. At least that's how I define it. I'm not sure. Yeah, none of it. No. So that was a typo. Anyways, let's. Yeah, so we were discussing originally that like we should represent numbers in terms of their prime factorization. The benefit was, okay, so I'll have this generic notation throughout this lecture, which is that I'll represent like AI is one of the numbers, let's say. I'll represent its prime factorization as this thing. A lot of people use this. Like it's a common way to represent. The idea being that all these PIs are primes and KIs are their powers. Right? So basically any number example, let's take 30, which is what? 2 into 3 into 5. So 2 to the power 1, 3 to the power 1, 5 to the power 1. Take another example, 45, which is 3 square into 5. So basically any number generically can be represented as, AI can be represented as P1 to the power K1 times P2 to the power K2, so on, which is basically like a concise notation will be this thing. AI to the power Ki, I goes from 1 to M, and let's just use AJ. So AJ is equal to this thing, right? So like always try to think of numbers like this. It generally helps for number theory questions. Example was LCM 1. So in LCM, let's say you have A1, A2, so on, okay? And each has a prime factorization. And let's say all the prime factorizations look like this. Let me give you an example. P1 to the, let's use R1 times P2 to the R2 times dot 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 PM to the RM. Then let's say A2 is also P1 to the S1 times P2 to the S2 dot 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 PM to the SM. Okay, in this one, I'm trying to use the same primes on the top and the bottom, because obviously one of them can be like, some of them can be like the powers can be 0. So if I have P1 to the power 0, that basically means 1, which basically means that P1 is not present. So example, maybe A1 is 30, right? So P1 is actually 2 and the power here is 1, but here also P1 is 2, but the power is 0 because this is 45 and 45 doesn't have a 2 in it. So it's just a way of representing. Now the LCM comes out to be pretty obvious after you see this, which is basically saying P1 to the max of R1 comma S1 times P2 to the max of R2 comma S2 and so on. So PM to the max of RM comma SM. Okay. The intuition being that you can think of each prime number individually. So just like instead of thinking 30 and 45, start thinking in some way of this sort. Yeah. So 30 has how many threes? It has 3 to the 1. 45 has 3 squared, right? And all the other prime numbers are completely independent problems. So you only care about this problem for now. And within these two numbers, what's the LCM? The highest power. Like 9 is the LCM out of 3 and 9. So this will contribute a 9. And similarly, this element will contribute something. This element will contribute something, so on. And you can just multiply them. You can multiply these guys because they're co-prime to each other. Here, 2, 3, 5, 7, 11, dot, dot, dot. All of them are co-prime to each other. That's why you can do this independently. That's why the max thing came out. Okay, and just to know, GCD, which is basically the highest common factor, comes out to be the min function on top, and so on. Again, so P2 to the min of R1, R2, comma S2, and so on. So that's the only difference. Here there's a max, here there's a min in the GCD and LCM. And notice, let's say you have A, which is P1 to the R1, dot, 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 PM to the RM. And let's say you have B, which is P1 to the S1 dot 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 PM to the SM. And we define LCM and GCD like this. What will LCM into GCD be? It will be P1 to the max of R1 comma S1 times min of, sorry, plus min of R1 times S1, right? I'm just using the formula above. In case anything is unclear or I'm going too fast or anything, just like put that on the chat. Okay, I can see the chat. Sorry. That's why LCM is different. Didn't get the LCM into GCD expression. Yeah. So, okay. So Naveen, I'll go through this again. Yeah. I think I went pretty fast on this. So LCM into GCD, right? What is LCM? LCM is P1 to the, we just now discussed max. So max of R1 comma S1, and then P2 to the max of R2 comma S2, and so on up till PM, right? Max of RM comma SM. And then this whole thing is the LCM, and then this is being multiplied by the GCD, which is what? Min of R1 comma S1. I'm not really going through the derivation of why the max and the min came. I gave you an intuitive reasoning of this thing, that all the primes are individually independent, and that's why you can just take the max power for LCM and min power for GCD, and P2 to the min of R2 comma S2, and so on, right, till PM. Again, you have the min. So RM to the SM. Now just do the multiplication. So you notice you can club these two guys together, you can club these two guys together, you can club these two guys together. So it comes out to be P1 max R1 S1 plus min S1 times P2 max R2 S2 plus min R2 S2. I mean, all the terms are pretty ugly, but yeah, you get the idea, right? And think about what's happening here. So if you have this expression max R1 S1 plus min R1 S1, like try out a few values, but it should be pretty obvious that it's going to be R1 plus S1. This is always going to be true, right? Because like, let's say R1 is bigger, then this thing will come out to be R1, and this thing will come out to be S1 if R1 is bigger than S1. And if R1 is less than S1 or equal to S1, then this thing will come out to be S1, and this thing will come out to be R1. Either way, the addition will be R1 plus S1. So in this expression, you can simplify this expression as saying P1 to R1 plus S1 times P2 to R2 plus S2, so on till PM RM plus SM. And you can break this again saying P1 to R1 times P2 to R2 times PM to RM as one entity, and P1 to S1 times P2 to S2 ... PM to SM as the next entity. And notice that this is actually A, this is actually B, so you got A into B. So you just proved that GCD times LCM is equal to A into B. I mean, that like the max and min are obvious because of this thing, because you eventually get this result that you want. And you can obviously try to extend it to multiple numbers also, like if you have like 3 numbers or something, right? I hope everyone gets the broad idea. I mean, the proof is really not relevant. The intuition that maxes and mins work for LCM and GCDs, and how we were able to solve the LCM problem by looking at the prime factorization of the number rather than the number itself. Like if you try to think about the number itself, doing like, you can like later on think about this, like how would you solve the LCM question if you just thought about the number themselves and not try to think about their prime factorization, and it's actually like relatively hard. It's not that straightforward because of integer overflows, and then you have this division by the GCD. Then you even need to know the Euclidean GCD method to get the GCD in the first place, and so on. Okay, so Rishi, like the key idea was that we are discussing the problem solving technique for intermediate up till intermediate number theory problems. I won't say this is applicable for hard number theory problems particularly. And the general idea being that you should try to represent the numbers you have in their prime factorization to get something useful out of it. Okay. So we just discussed how LCM is, like how you can do LCMs using the max power on the exponent and the GCDs using the min power on the exponent. Yeah, this is going to be uploaded on YouTube, so actually we shouldn't go through again. Okay, so the next question was, is a number square free or not, right? So you have this number x, let's say, and its prime factorization is again p1 to the k1 times p2 to the k2 times ... pm to the km, right? And you wanted to identify whether x is square free or not, right? And what was the definition of square free? That all factors of x should not be squares. Okay, so let's go. Okay, first forget about this thing, like that you can represent them in their prime factorization. I mean, somebody did get in, Jacob got it in the comments, and it's straightforward. But if you didn't think about the prime factorization method, what would you probably do is, okay, the first approach that people would try would be to iterate over all factors, basically pick all the factors, try all the factors and see whether they are square numbers or not, right? The complexity of this thing will be number of factors of n, right? And for each factor, you will have to actually see whether it's a square number or not. That's generally done pretty fast because you can calculate, use the square root method, and then just get the square root and square it again to check whether you get the same number or not. Let's say you want to check, is 10 a square number or not? Then what you can do is you can just do square root of 10 int y is equal to square root of 10, right? And then you say, if y square equals 10, then it's probably square. Otherwise, it's a not square. That's it, right? Obviously, this is not like, this is reasonably fast in the square root method, but it's still not O1. But yeah, it's good enough. So the complexity will be order number of factors. Okay, another question you can answer in the chats. What do you think is this thing? Like, if I have a number n, how many factors does n have? At most. Anyone? N by 2. Okay, I mean, that's a pretty loose bound. Obviously, a number won't have more than n by 2 factors, but do you have a tighter bound? Okay, Saurav said square root n. Okay, Preet also said square root n. Okay, square root n in general is a good bound. A lot of people use it. I would still not recommend you to use it a lot because even square root n is not tight enough. A more accurate estimate is generally something like log square n. I won't go into the details of why I think it's a log square n or something of this sort, but basically just the takeaway is that it's generally not square root n. Okay, I'll give you the rough intuition of why it actually never hits square root n. So let's say you have this number n and you think that it has square root n factors, right? So let's say for simplicity, you think it has, okay, let's say you think that it has 2 square root n factors, okay? What this means is that within the numbers 1 to square root n, there will be root n factors, right? And from the number root n to n, there will be another root n factors for this number. But like basically half of the factors should lie before the root nth step and half of them should lie ahead of the root nth step. The reason is because every factor should be paired, right? Example, let's take n equal 100. Then like you say basically the factors between 1 to 10 and between 10 to 100. So 10 is a square, so just ignore that. Let's say 2 and the complementary guy is 50. Then there is 5 and the complementary guy is 20 and so on. Basically all the guys before the square root value have a complementary guy ahead. The 2 matches with 50, the 5 matches with 20, right? So the idea is if you want to have almost 2 square root n factors of a number, you need to have square root n factors here and you need to have square root n factors here. It's not easy to come up with a number whose basically which has all the numbers as factors up till root n. Okay, let's take an example. Let's take an example as, I don't know, 360. No, let's keep it simple. Okay, 3600. Yeah, n equal 3600. What's the square root? 60, right? So what you want is that from 1 till 60, every number here should be a factor of n. Every number should be a factor of n. Now you can easily notice that this is not going to be true. Every number should be factor of 3600. Only then you'll get something like 2 square root n factors, right? Only then. Okay, yeah, Bhagya is right that log square n is not a, I mean, you're correct that log square n is not a tight bound, but the idea is don't think of calculating the number of factors as expensive as root n. A lot of people, what issue they have is, or like what bugs they make is that during a contest, they have a solution or an approach to a problem, but they think that root n will be too costly here because they think that the number of factors is root n. So they actually plug in root n in all their formulas and they get that, okay, the thing goes above 10 to the power 8 operations per second. So they don't implement it also. And that's the issue, that don't think of it as square root n because if you start thinking of it as always a square root n, you might not implement an algorithm that you think will be slow, but it's actually fast enough. So here, now think about this. Can you get every number to be a factor of 3600? It's very hard. I mean, in this case, it's not possible, because think about this. All the numbers that are primes in this range, example 2, 3, 5, 7, 11, 13, 17, 19, blah, blah, blah. These guys need to be factors of 3600. And for all of them to be factors of 3600, 3600 must be something like 2 into 3 into 5 into 7 into 11 into 13. Basically, it should be like LCM of 2, 3, 5, 7, 11, blah, 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 right? It should be a multiple of these guys. And the LCM of prime numbers is just the product. So you can see that this thing explodes pretty fast. So you actually don't get square root n factors, like in most of the cases. You can try to come up with numbers and see how many maximum number of factors I can get, and you will generally not hit this value. Maybe for specific n's, you'll hit a very big value, but in general, you will hit something like log n or log square n or something like that sort. So it's not going to work in every test case, will it? Okay, one, that's a good question. So yes, if a question asks you for a specific n, then you should think of it as square root n. That, okay, he'll give me the worst n. But sometimes what you're doing is you're doing from 1 to n, do something like order number of factors of I, and I goes from 1 to n. Here you are effectively doing from like number of factors of 1, number of factors of 2, number of factors of 5, so on, up till number of factors of n. In this case, it's not actually going to be n root n. Some people think that it's going to be n root n because each guy will have root n factors or something. This is going to be more or less like n log n or maybe n log square n, but nowhere near n root n. It won't be that expensive. You can actually run it on your computer and test. Okay, Devansh, we'll come to that later. But that how do we calculate the number of that? How do we calculate factors? Yeah, we'll come to this later. But square free numbers. So this was the first approach. What was the second approach? The second approach would be, you guys might have thought about it, I don't know. Put all the square numbers in a set. Put 1, 4, 9, 16, 25, 36, 49, so on in some set of some sort. And then basically just test each number. Is it a factor of n? X, sorry. Is 4 a factor of x? Is 9 a factor of x? And so on. Basically, for each square number, test whether it's a factor of x or not. Right? That's the other crude method to solve this question. Square free or not. But both of them are going to be actually slow. This one is going to be roughly order square root x. Because you have square root x prime, if x is going to be, let's say, 100, then you have around 10 square numbers below 100, which if x is something generic, then you have square root x square numbers below x, which are less than equal x, and that's why it's going to take square root x time. The prime factorization method, which someone mentioned in the comment in the chat, was basically, if you have the prime factorization of the number, you can just see each power and see whether all the powers are less than 2. If all the powers are less than 2, you're done. Then it's a square free number. But if any of the power is greater or equal to, then it's not. The reasoning is this. So you had x, right? And let's say x is 45. So that's 3 squared times 5 to the power 1. Now you see a square here. Okay, the square actually doesn't matter. Let's say it's something like this. I'm just creating a number out of the blue. Let's say this is the number, right? 2 to the power 5 times 3 squared, blah, blah, blah. Now notice it has 4 as a factor, right? Because it has 2 to the power 5, which is 32. So obviously something smaller than 32 and a power of 2 is also a factor. So this number has 4 as a factor. So it's not a square free number. If this thing is anything greater than 2, let's say it's 2 to the 10 times blah, 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 something, then also it has 4 as a factor, right? And if it's 2 to the 1, then it doesn't have 4 as a factor. Then you move on to the next guy, 3. If it's again a 1, then it's okay. But if it's a 2, then you see that, okay, 9 is a factor. So it needs to be 1 again, and so on. Maybe there is no 5. Maybe there is directly the next guy is 11. And maybe he's coming 3 times. Then you know 121, which is a square number, is a factor. So it actually needs to be 1, 11 to the 1. Otherwise, it's not a square free number, right? and you can't create. Okay, now you might be thinking that, oh, but you've only considered p squares where p is prime. I haven't considered those square numbers which are like not of prime. Example, I have, let's say 10 square, 100. Maybe 100 is a factor of n, is a factor of x, right? Maybe. Then have I considered it? But wait, if 100 is a factor of x, then definitely 10 square is a factor of x because it's the same thing. And if it's 10 square is a factor of x, then definitely 5 square and 2 square, both are factors of x. So you actually don't need to test 100 because if 5 square and 2 square, if either of them is a factor of x, it's definitely not square free, right? And if both of them are not present, that is the power of 2 is less than 2 and the power of 5 is also less than 2, then we know that 100 is not going to be inside. Devansh asked for 16. Can you elaborate this? I don't get what you mean by 16, Devansh. 10 to the 100. Okay. So, okay, in the above method, okay, like don't do this prime factorization thing blindly, like in every question that I'm going to prime factorize things. Don't do this blindly. So you have to think about why this method works. We saw that, okay, so we were able to discard things, right? And we ensured that the power should be 1 or like 0, right? Of all the prime numbers, the exponent should be 1 or 0. But we didn't consider the case, okay, we only consider, so we were only able to eliminate those cases where the square number is of the form p square, where p is a prime. So it's like 4, 9, 49, something of this sort. Basically 2 squared, 3 squared, 7 squared. Basically these things are primes, right? But what if it's like 10? 10 is not a prime, right? 10 is not a prime. And but 100 is like a square number. So will our method work if 100 is a factor of the thing? Let's say our number is 300. Okay. Now, obviously 100 is a factor. So technically our program should print that it's not square free because 100 is a factor of 300. Now, will our program actually catch it? Yes, it will. That's what I was trying to explain, because if 100 is a factor, then definitely 5 square and 2 square are also factors. And because 5 square and 2 square are factors, therefore in the prime factorization of 300, these guys will come. So you'll actually catch 4 here and 25 here. So because you caught these guys, you know, okay, 100 is also a factor. You don't really care. Basically, if 100 is a factor, then smaller square numbers are also factors. That's the key idea. And that's why this thing works. Yeah, if k square is a factor of n where k is not prime, then x square will also be a factor of n where x is a prime factor of k. Yeah. So I just took the example as 100. Sir, wasn't it supposed to be DSA? I mean, this is kind of like, okay, this is not purely DSA. This is more like, I mean, the today's topic is math, so I can't help it. Yeah. But I mean, okay, the next, like, I mean, the next sections will be more about the implementation, but at least I wanted to cover the theory first. That basically the broad idea that you should always, like, at least for simpler questions, always try to think about the prime factorization of the number. It can be represented as product of primes and then check for the powers of factors. Yes, Omesh, you're correct. Yeah, that for composite numbers, you can basically break them into primes and then again think about like those guys. Okay, so let's move on. If you have like more detailed questions, you can like keep on asking. Yeah. How to represent them? Okay, so now we discussed all these methods, and in all these methods, we had this thing that, yeah. Okay. So you can see my screen, right, guys? Yeah. So in all these methods, we had this thing that we can represent numbers fast in their prime factorization. Can we talk about some DP questions? Onkar, this is actually a number theory session, so I don't think we'll be discussing much DP. I think the DP session will be like probably in the next week or something. Yeah. Sieve should work for factorization. Yes. So like the next step will be basically I'll be showing the implementation of like basically in the about like in the previous whiteboard thingy, we all saw that okay, we like given a number, a lot of times we have to represent the number in its prime factorization, basically get all the prime factors and what are their respective powers, right? But how do you do that fast? That's the question. So I'll show you some ways to do this fast. I mean, I'm going to pretty much implement it from scratch. I mean, this is probably the fastest way in general. So we'll be creating a sieve. I hope everyone is like broadly familiar with the sieve of Eratosthenes. Yeah, the Eratosthenes thingy. So and let's just pick a constraint like 26ish, right? So if the number is composite, okay, because I declared composite array in the global, this is going to start with zeros, that is falses. Okay, and then you basically go through each number, and if the number is composite, so yeah, let's say you start with I equal 2, and then if the number is composite, you skip it. Otherwise, you say pick. Okay, I'll go through this. I'll go through this since people are saying that we need to go through this. Yep, and let's put in some more things. I'll first write the broad code and then you can. Yeah, so this is like, that's like the more or less the entire code of the normal sieve at least. We'll come to the factorization part later, but like that's the default code. So how the code works is basically, think of the composite array. This is the important array. The vector primes is not really that important. Now, when you come in for I equals 2, right? This thing is false because the entire thing is false. So this thing doesn't get triggered. Now you ignore line 15 for now. This is just a trivial line. Basically, if this thing doesn't trigger, that means this I is prime. If I reaches line 15, that means I is prime. Okay, so you just push it in the primes vector and you basically collect all the primes there. Now, okay, since I is prime, definitely 2 times I, 3 times I, 4 times I, dot, 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 all these are not prime, right? Because all these have factors as 2 and I, 3 and I, 4 and I. Like, how can 4i be prime when 4 is a factor of 4i and I is also a factor of 4i? For 2, in example, for 2, if 2 is prime, which we know it is, then 4, 6, 8, 10, basically all the multiples of 2 can't be prime, right? And to say the statement more rigorously, what you do is you run a loop from 2 times I till n, and you increment each time by I, basically. Sorry. The fuck? Okay, sure. I lost the code. Sorry. I'll just quickly write it again. Oh, my bad. Yeah, someone actually posted the code also. I mean, there are a lot of implementations. I just write this one because I find it simple, and like you can use some other implementation also. Just like, yeah, till the time you understand the implementation, just use any. Okay. So I think this was the broad code. I won't be compiling this code, but like, yeah, this works. Okay. So yeah, right. So here when I was 2, we basically said 4, 6, 8, all these guys are not prime. To say this more rigorously, we are saying 2i, 3i, dot, dot, dot are not prime, right? And here basically j goes from 2i, 3i to blah, blah, blah. Notice that j is actually not being incremented by 1 here, but it's being incremented by I, and it starts from 2 times I. So here actually the thing will go like, basically you'll flag all these guys as false. So you'll say composite 4 equals 0, sorry 1, composite 6 equals 1, and dot, dot, right? And then in the next iteration when you'll come, you'll see 3. So when I is 3, that means 6, 9, 12 are not prime. That means here composite 6 equals 1, blah, 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 right? And then next time 4 comes in. What happens with 4? Okay, so actually you have already set composite 4 to 1. So this statement will trigger, right? For I equal 4. The statement will trigger and you won't put it as a prime. Also, you'll save complexity here because the continue happens. So you won't execute this inner nested loop. That's also another saving here. And this method works, right? So in case anyone still has doubts, like go through the Wikipedia or ask if your question is trivial enough. The complexity of this thing, what's the complexity? So when I was 2, how many steps did you take? You looped through 2, 4, 6, 8, blah, blah, blah. How many steps does it take? This takes n by 2 steps. When I was 3, how many steps did it take? It took n by 3 steps because it ran from 3, 6, 9, 12, blah, 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 right? So it's actually taking n by 2 steps. Then in the next time it's taking n by 3 steps. Then it's taking n by 5 steps, not n by 4, because when I was actually 4, this thing skipped this. When I was 4, line 13 got triggered, and that's why you never went to line 18. So n by 5 plus n by 7. Again, 6 won't be triggered because it will be composite. So basically, all these numbers are going to be primes that I'm adding here, right? And this thing is basically equal to, in the complexity analysis session also we did this, which is basically equal to this thing, right? 1 by p in general, where p is prime, right? And this thing actually comes out to be order n log n. For more practical purposes, just think about it like 5n. Yeah, because think about it. If n is even like 10 to the 7, which is probably the biggest value you'll get in comparative, then log of n is going to be probably be 7 into log 10, which is something like 21. And then log of 21 is going to be something like 4-ish. So I'm doing all these logs base 2. Yeah. Devansh asked something, but I don't get the question. Can you please the second loop again? Okay, I hope you're saying explain. So on line 18, what's happening basically is that in the nested loop, you're basically saying that, okay, you're saying if I is prime, then 2 times I, 3 times I, dot, 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 all these are not prime. So you're basically saying if I is prime, then 2 times I, 3 times I, dot, 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 all these are composites, right? Because they're not prime, so that means they're composites. Exclude the one case, we never went through one actually, because I started from 2. Because that's what we are doing. So when we got that I is prime, because we ran till line 14 and the line 13 didn't get executed because we are prime ourselves, we strike off all the multiples of ours. We strike them off. Okay, so I think there's a very good visualization of sieve of Eratosthenes. Like, yeah, just like going through the code is sometimes mundane, but I think there is some fancy GIF online available which actually shows you how the thing works. Yeah, so here's the GIF. I hope you guys can see this. So when 2 is prime, you basically strike off all these guys, all the multiples of 2. Striking off in our code means setting the composites as 1. When 3 is prime, you again strike off all the multiples of 3, which is 6, 9, 12, 15, blah, blah, blah. Obviously, there will be duplicates. 6 got striked off twice, 9 got striked off once, but 12 got striked off twice, once because of 2 and another time because of 3. But like, it doesn't matter if a number gets striked off twice, right? And so on. So that's the idea. Does everyone get this? Like, you can just run through the animation again and like, yeah. So is everyone clear with the basic sieve of Eratosthenes? Okay, Bhagya is saying square root in first loop. Yeah, you're correct, Bhagya, but like, it honestly doesn't matter much. I mean, some people do that, what you're saying, but like, Okay, so even this thing works if someone is curious to see. Yeah, this thing works. Yeah, what Bhagya recommended, that you can do this and like this works, which goes basically till blah. I goes from 2 to square root n. This doesn't mean that this is faster than order n log n. It's still as slow as n log n. It doesn't get faster than that. Yeah, just so you know, it's not order square root n times something. Yeah, in case somebody starts thinking that way, because you still summing like the complexity comes from this part, from line to 19 to 23. That's the where the actual costing comes in. So you're actually still getting n by 2 plus n by 3 dot dot dot. Obviously, you're stopping this thing at square root n-ish. You're not going beyond this, which is a good thing now. But it's still going to be order n times 1 by 2 plus 1 by 3 dot 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 up till 1 by square root n-ish term, which is still roughly n log n as far as I know. But yeah. So don't think of this optimization as being considerably faster, but yeah, it's faster. And I won't go into the detail of why this works. So we'll stick with the original one for now, because I don't want to go into the detail of why that thing works. Okay, so shouldn't J be till less than N? I mean, okay, yeah, fair enough. I mean, now you can do till equal. There's no memory leak. Earlier there was a memory leak. Right, Korea? Why is it J? Okay, I mean, you could do 2 times I. I just didn't write that way, but like, yeah, the idea is that J should go from 2 times I, 3 times I, blah, blah, blah. J should iterate on the multiples of I. That's the idea. Okay, Bhagya is again right, yeah, that you can start with I square. But like, so yeah, like you can search up on the internet. There are actually pretty, like much more efficient implementations of sieve of Eratosthenes. This is the most basic one, but like, as far as I know, this never TLEs. Yeah, I haven't seen people actually getting TLE on this implementation. But yeah, Bhagya is correct that there are more efficient implementations. Like one of them basically starts this thing with I square. The idea being that, so you actually don't need to start from 2 times I because some things are already crossed out. Yeah, but I don't want to go into the detail. I mean, it's a good hack if you want to know. You can read about it on like some Code Forces blog or something. But like we won't go into through that. So anyways, we wanted to go through how do we factorize number fast, right? So one method here is that instead of having a composite array as a bool array, have it as an int array. Okay. And if the composite of a number is 0, then sorry, if it's non-zero, then you continue because it's a composite number. Otherwise, you know it's a composite number because this thing gets initialized to 0, right? Okay. Instead of composite, let's name it. Let's rename this to something more suitable. Prime factor. Okay. Yeah. So otherwise, what you'll do is like there's just a slight change. Yeah, that's the main change. That's it. Now, what I'm doing is I'm saying, okay, J's prime factor has been set to I. So what I'm saying is, okay, after this thing runs, your prime factor array will probably look like this. So we don't care about the 0th value. Let's be -1. Okay, it will be 0 actually. 1 will also be 0. 2 will be 0. What will 3 be? Again 0. What will 4th element be? 4, value 4. Value 4 will be 2. Value 5 will be 0. Value 6 will be 3. Now think about this thing. Value 7 will be 0. Value 8 will be 2. Value 9 will be 3. Value 10 will be 5. And so on. Carefully think why prime factor 6 is going to be 3. Why prime factor 8 is going to be 2. Why prime factor 10 is going to be 5. Just think about these guys. So the idea is whenever you set that, oh, I is a prime number. So here I is prime, right? We set all the multiples of I to start saying that, oh, I is my prime factor. Okay. So 6 will say, okay, so after some run, it will come out that prime factor of 6 is actually 2. Like here, you start saying that prime factor of 2 times, 3 times 2 is actually 2, right? When I is 2, right? But in a future iteration, when I is 3, you'll start saying that this is actually equal to 3. So this is going to, so prime factor of x is going to be the largest prime factor of x. Does everyone get this? Because the value in this position is going to be overwritten again and again till the time we are able to find the prime factor of j. Let's say j is 10. We found the first prime factor at 2, so we wrote 2 here. Then we found the second prime factor as 5, so we wrote 5 here. So it actually got overwritten to the largest one, right? So that's how the prime factor array is defined in our case. I hope everyone gets what's the definition of prime factor array and why it's so. This is important. Now the next step is pretty simple. What you do is, okay, also notice you need this line also. That is, if I is prime, then its prime factor is the number itself. Prime factor of I is I itself, right? Now you set int x equal I while x is not equal to 1. I'm hoping everyone is comfortable with maps by now. Mx. Let's see. What should we do? What should we do? M prime factor of x and x divided by equal to prime factor of. Okay, I didn't motivate my code enough. So eventually what we want is, yeah, let me motivate it. What we want is, right? We want to fill the structure. Vector pair int prime factors n plus 5. What prime factors 10 should store is basically, let me give an example, like 45 is a good example, right? So this should store a vector whose first element is 3, 2, next element is 5, 1, and this is the entire vector. We want prime factor 45 to store this. What this means is 3 squared times 5 to the 1, right? 3 squared times 5 to the 1, which is equal to 45. So the first element of the pair is going to be the prime number. The second element is going to be the exponent. The first element is going to be the prime number. The second element is going to be the exponent, and we'll have a vector of this thing. Okay, so everyone got what I want to store eventually. That's how we represent our prime factorizations, right? I mean, this is one of the most efficient implementations, like most efficient way to represent your prime factorizations. Once you have these vectors, you can do the GCD, LCM things, or the square free thing. Like if you have this thing, you can easily do the bool square free method. Let's say you have x. What will you do? You'll simply iterate on the vector of x, right? And say if v dot second is greater than 1, then return 0. Otherwise, return 1. Okay, so somebody asked me to explain in Hindi. Okay, so थोड़ा बहुत कर सकता हूँ explain. Broad idea पिछली बार ये था कि एक prime factors का data structure store करना चाहते हैं, which is this thing. So the idea being that कि एक vector होगा जिसमें हर pair store करता होगा एक prime number और उसका कितना exponent है. इधर 3 square times 5 की पावर 1. So 9 into 5, 45, right? When you do this, the square free method becomes pretty easy to code, because notice now you just have to iterate over the entire vector for 45. For example, 45. So पहला auto v में पहला pair क्या आया? 3, 2. So you just have to check whether the power is greater than 1 or not. If the power is greater than 1, then square free नहीं है. Otherwise, the number is square free. So you return a 1. Otherwise, you return a 0. Okay, returning 1 and returning true are the same thing. You can just write either. I just prefer to write 1, 0. But like, yeah, it's the same thing. Some people get confused here. So, okay, you have a map. So we want to make this data structure at line 7. We want to create this thing, right? So I'll remove some comments here because I mean it's unnecessarily big. Or yeah, so that everything is visible in a single line, in a single. Right? Yeah, everything should be visible in a single stance. So we have a map. Map क्यों है? to increment the things. So we get the prime factor and we increment its occurrence. So basically M of 3 will store how many times has 3 come in prime factorization of I, right? And generically mx will store similar thing. Mx will store how many times has the prime number x come in the prime factorization of I. Okay, so jab tak x 1 nahi jata, while x is not equal to 1, we say take the prime factor of x and increment its frequency and divide x by its prime factor and just keep on doing this. And eventually what you do is you do prime factor I dot push back v dot first v dot second. Yep. So this is pretty much the code. I'll go through a run of like an example I. So let's say I is equal to 45. I like 45. So x is also 45, right? Because I start x as 45. Now the map is empty initially. Till the time x doesn't go 45 or doesn't go 1, we run this thing. So what happens the first time? We say m prime factor of 45. What is the prime factor of 45? What did we define as prime factor? The largest prime factor of 45, which is 5. So m5 plus plus. This is what happened here. And then we said 45 divided by 5. So x became 9, right? In the next iteration, x is still not 1. So what will happen next time? Next time, m prime factor of 9, which is what? Which is m3 plus plus, right? And 9 divided by 3, which gives x equal 3, right? Now what will happen? Here x is still not 1. We'll again get m prime factor x plus plus, which is again m prime factor 3, which is m3 plus plus again. Okay, notice why I did this thing, why this is important. Because prime factor of a number itself, like if I is prime, then its prime factor is the number itself. This line is that's why important, because when you got prime factor 3 here, you actually want this thing to be 3 itself. This prime factor 3 should actually be 3, right? That's why that line was important. If you missed it, you'll have some bug. So m3 plus plus happens, and then next time 3 divided by equal 3 happens here, which makes x 1. And once x became 1, you break, because your loop was only going till the time x was then 1. So this is a common way to write this thing. And using maps just simplifies the implementation. Somebody in the comments also suggested that we can use vectors, but like in general, using vectors here becomes slightly tricky because you have this prime factor thingy, and yeah, it becomes slightly tricky, but you can implement it. It's just like this is more concise. That's why I prefer this one. But like, yeah. So let's just write homework. Use vector instead of here. Shivaram Prasad Misa. Okay, you're somewhat correct, but like the idea is much simpler, Shivaram. So what you're saying is also correct, that the number won't come again, or at least it will come again. Like if you're starting with x and let's say its largest prime factor is 11, then 11 will come a bunch of times, and then something smaller will come. Let's say 5 will come, and then 3 will come, and 2 will come, and it'll just be finished. The idea is something simpler. The idea is if you have x equal, let's say 100, I don't know, 360, prime factor of 360 is one guy, which is a prime factor of 360. It might be 2, it might be 3. We don't honestly care. It just needs to be one guy. We don't honestly care whether it's the largest guy or not. Even if it's not the largest guy, so even if prime factor x is not the largest prime factor of x, the thing still works. Basically, prime factor of x should be one of the factors of x. prime factors of x. So let's say prime factor of 360 actually came out to be 3. Then we know that, okay, one of the prime factors of 360 is equal to 3. So that means how much remaining number do we have to calculate? We know 360 can now be written as 3 into the remaining portion, which is what? 120, right? So 120. So problem got reduced to finding prime factorization of 120. That's it. If you can find the prime factorization of 120, then you can find the prime factorization of 360, right? Just plug it in here, whatever the prime factorization of 120 is. If you got the prime factorization of 120, then you can just say 3 into that prime factorization and we're done. So now again, to find the prime factorization of 120, you'll again ask, what's the prime factor? Just you'll ask, give me one prime factor of 120. Maybe it gives you 5. So you know 120 can be written as 5 into whatever, 12? No, 24. And then you'll again ask, prime factorize 24. That's the way the method works. Basically, for each number, you need at least one prime factor of that number so that you can drop that number. And once you've dropped that number, you can keep on doing it again and again, because for each number, you know one of its prime factors at least. So for 24, you'll know prime factor of 24 will have, let's say, 3. So now you know 24 can be represented as 3 into 8. For 8, you'll know prime factor of 8 is 2. So you know 8 can be represented as 2 into 4. For 4, you know prime factor of 4 is equal to 2. So you know 4 can be represented as 2 into 2. Now for the last 2, prime factor of 2 is actually 2 itself. So you know 2 can be represented as 2 into 1 and you're done. So now you can just backtrace this. 8 can be written as 2 into 2 into 2. 24 can be written as 2 into 2 into 2. This can be written as 3 into 2 into 2 into 2. And yeah, I mean, this got complicated pretty fast, but like, yeah, this can be written as. So, I mean, don't try to, I mean, this is a live session, so I'm going slightly fast across this stuff, but like, still try to get the rough idea of why things work in this manner. Here, the thing work. Let's not delete this. Yeah, let's just keep this here. So, did everyone get the broad idea? We're actually lagging behind because like it's still, I mean, yeah, we're actually running quite slow. So I think we should speed up. Okay, Pallavi, can you put on the discussion section, like the poll question? Okay, so we did the implementation part. Now, the next question that we want to do is solve KPRIME, right? And after that, solve CHMOD, maybe, hopefully. Yeah, but like, okay, so this is an audience poll. Okay, we'll definitely solve KPRIME. I think we have enough time to solve KPRIME at least. And I want to do one more theory topic. If we are running short on time, we can probably skip solving CHMOD. So these are like the 3 things that I'm asking people. Like either we can discuss the math block questions, or we can discuss fast matrix expo, or we can do modular arithmetic for classical and non-classical use. Cool. So we'll do fast matrix expo. Right. Okay. So for fast matrix expo, I mean, I'll go through the key idea and the binary exponentiation thing, and I won't go through the coding aspect. I'll just go through the theory on iPad, and I won't go through generic recurrences because that's part of DP, and like I'm not expecting everyone to be able to get all the DP-ish thingies in this, but obviously we'll cover the Fibonacci and like the basic ones. But like another hard aspect of like good hard fast matrix expo questions is that you need to be able to form that recurrence. For Fibonacci, we are already given the recurrence, so it's relatively much simpler to do. But yeah, okay. So we'll quickly go through the question that we have, which is KMOD-ish. Which question is this? Yeah, K-prime. But yeah, okay. So a number is K-prime if it has exactly K distinct prime factors. Okay. Distinct prime factors and exactly K. Although a prime factor can be occurring multiple times. Like it can be like 2 is occurring multiple times, like 2 into 2 into 2, but like it's still a single prime factor, right? The game is quite simple. Alice is given 3 numbers A, B, and K, and K prime factors between A and B, both inclusive, blah, blah, blah. So between the range A to B, how many numbers are there from A to B, which are K primes, right? That's the question. And T test cases. So you're given a lot of test cases. So it's expected that you solve each test case pretty fast, like O1, maybe O square root this thing, maybe like, yeah, basically O1, O log n or something. Not much slower than that, right? Notice that k is less than equal 5. So this is the first obvious hint in the question that if you see any constraint which is like super small, then you can probably exploit that, right? So in this question, the exploit comes from the fact that, okay, so what did we discuss before? That try to represent each number in its prime factorization, right? So let's say we have all the numbers from 1 to n beforehand, and we represent each guy in its prime factorization. So prime factorization of first guy is 1, 2 is 2, 3 is 3, 4 is 2 into 2, 5 is 5, 6 is 2 into 3, so on. Now we can even store their k factorization, right? Basically, we already wrote the code for like how to get the prime factorization of each number, right? So we just need now 1, 2, 3. Okay. Basically, A array will be, so I'm going to define an A array such that A is going to be how many distinct prime factors does I have. So how will the A array look? Ignore 0. 1 will have 1 prime factor. Ignore 1 also actually. 2 will have 1 prime factor. 3 will have 1 prime factor. 4 will have 1 prime factor. 5 will have 1 prime factor. 6 will have 2 prime factors because 6 is 2 into 3. 7 will have 1 prime factor. 8 will have 1. 9 will have 1. 10 will have 2 because 10 is 2 into 5. 11 will have 1. 12 will have 2 because 12 is 2 squared times 3, right? And so on. That's it, right? Abhilash is asking, I'm struggling, blah, blah, blah. Abhilash, honestly, I would recommend you to switch from Python to like C++, Java or something of that sort. I mean, I'm personally not that confident in Python, so I don't know how do you take input in Python. I mean, there is raw underscore input to take generally input in Python, and then you have to typecast it to strings or something. Like typecast those strings to integers or something. But in questions, in a lot of questions, the issue comes that the raw input is also slow or like you need some custom hacks. Basically, for example, in Java, you need buffered custom IO buffered reader or something. So even in Python, you have the same issue that you need a lot of details to actually get it working. Like to be able to be fast enough to actually get an AC in competitive programming. Otherwise, I think it's a pretty good thing, but yeah. So, okay. So yeah, once we got the A array, now we know that k is less than equal 5, right? In this question. Because k is less than equal 5, what you can do is, okay, now you have this A array, which is basically how many distinct prime factors does I have. Now let's say someone asks you that L is 10, R is 15, and K is 3. What this means is that from 10 to 15, how many numbers in array A have value 3? Right? That's the question, right? I mean, if in the original question, let's say your L was 10, your R was 15, then the question basically becomes in your array A. Okay, sure. So होना the question ये था कि एक array given है हमारे पास and हर नंबर की एक मतलब हम नंबर को बोलते हैं कि वो k प्राइम है या 3 प्राइम है या 4 प्राइम है अगर उसके 4 डिस्टिंक्ट प्राइम फैक्टर्स होते हैं या 3 डिस्टिंक्ट प्राइम फैक्टर्स होते हैं एंड देन क्वेश्चन आस्क करता है कि L से R की रेंज में कितने ऐसे नंबर्स हैं जो एग्जैक्टली k प्राइम है लाइक एग्जांपल देता हूँ L 10 है R 15 है k 3 है तो मतलब 10 से 15 की रेंज में कितने ऐसे नंबर्स हैं जो 3 प्राइम है और 3 प्राइम का मतलब क्या है all those numbers whose prime factorization have exactly 3 prime distinct primes. In this example, like 12 के 2 ही प्राइम नंबर है तो वो 3 प्राइम नहीं है 12 is not 3 prime. But 10 is also not 3 prime. But let's say let's take an example 2 into 3 into 5. 30. 30 is actually 3 prime because 30 ki prime factorization देखो 2 into 3 into 5 3 distinct primes are. Cool. So how many okay, so the same question can be remodeled as saying from the range L to R, from the range 10 to 15, how many numbers have value in array A have value 3, right? Because our array A is defined as like k primes. Basically, AI is equal to this, which is basically k prime value of I. Right? That's how our AI is defined. So assuming we have this magically, we have created this A array magically for now. Don't think like how will we create this A array. But once we have this A array, the question is pretty simple. It's just asking from L to R, how many numbers in array A have the value 3 or have the value k, right? But we know k is less than equal 5. So question reduces to given a range L to R, how many numbers in this range have value k in array A. K is less than equal 5. Okay, L and R are pretty big. That's it. That's the question, right? Ab ye question pad ke, okay, what are the hints? There are no updates in this question, right? There are no updates. So don't think anything complex. Don't think segmentaries because there are no updates. Agar question mein updates, so only then think segmentaries. If the question doesn't have updates, it probably has a simple solution. So you since you're not going to use segmentaries, but you still have to calculate a range thing, like so you can do prefix sums. So basically, how many numbers in the range 1 to R have value k in array A minus how many numbers in range 1 to L minus 1 have value k. Okay, Redmi is asking, oh, Redmi phone. What does update means? Okay, in this question there are no updates, so don't think about it much. But like, I assume some people like here will be familiar with segmentaries and they might start thinking from the segmentary angle. If you're familiar with segmentaries, there's a very high chance that you'll start thinking from segmentaries angle. If you're familiar with segmentaries, and an easy way to not go down that rabbit hole is by questioning key, are there any updates in the question? Because segmentaries are generally used when there are updates, basically when values in the array are being changed. Yeah, so update basically means values in array A are being changed, right? If there are no updates, then generally you can find something simpler than segmentaries. Something simpler generally works if there are no updates in the question. So that's why I'm just saying that if someone is thinking segmentaries, it's a good idea not to think of segmentaries because there are no updates in this question. So we'll actually do it by prefix sums, because this question can be remodeled as saying how many numbers in the range 1 to R have value k, and then subtract, which is basically minus sign, how many numbers in the range 1 to L minus 1 have value k. This will give you L to R answer, correct? This will give you L to R answer is equal to this thing, right? And you know that value of k is at most 5. So if for value equal k equal 1, you have this prefix array, which is basically prefix I k denotes how many numbers in range 1 to I have value k in array A. Let's say you have created this prefix array. Then answering is simple. If the question comes LRK, you can simply print out prefix RK minus prefix L minus 1k, right? Like given you have a prefix IK, prefix a 2D prefix array defined like this, such that prefix IK is actually this thing, that how many numbers in the range 1 to I have value k in array A. If this is how your prefix IK is defined, then your answer is pretty simple. For LRK, just print out this thing, because like, so this thing is basically equal to prefix RK, right? And this thing is equal to prefix L minus 1k, and I'm just subtracting these two guys, right? So is everyone clear with the broad idea of the question? That originally we had this question. First we said कि we'll create this array A, which is basically हर number का K prime. What's like get the K prime value of each number. And then we'll say the question is reduced to finding in the range L to R occurrences of a specific value K in this array A. That's the question now. Like we can just rephrase this question. And then this thing is equal to numbers in the range 1 to R, whatever answer we get, minus numbers in the range 1 to L minus 1, whatever answer we get. We'll subtract these two guys and we'll get our answer. And this thing can be represented as a prefix sum. So that's why I'm using prefix IK here. I hope this is clear. In case you have any doubts, just put it on the chat. Yeah, like I'm not sure if this is going to be clear to people or like how many people. Okay, so I think it's clear to people. Okay, nice. Flame asked a good question. That will memory be a constraint here? So the way the reason why this method actually worked was because this thing is actually pretty small. This is actually consuming just nk memory, and we know k is less than equal 5. So this is actually order 5n memory, and also order 5n time. Like creating the entire prefix nk this thing 2D array will actually take order 5n memory and space because k is small. Had k been bigger, this would have been an issue. But since k is small, this is pretty fast. Creating this prefix 2D thing is pretty fast. Okay, can you explain the time complexity again? So I haven't really talked about how you will create this prefix ik. This is more like this. Prefix ik is equal to prefix I minus 1k plus ai equal k. This is going to be the recurrence that we are going to use, right? Key till I minus 1, whatever we had, just add that. And is the current elements k prime equal to k? If yes, then add a 1. If no, then add a 0. This thing is going basically here ai equal k is going to be 1 if ai matches k, going to be 0 if ai does not match k, right? And so you have this recurrence, right? And now complexity is what? The dimensions of the two things. Basically, how many values are being calculated here. So it's going to be order n times k. That's how many values are calculating. And that is equal to n times 5 because k is less than equal 5. Yeah, Aryan has a good homework question. So a homework question can be, which Aryan just proposed, that if k is reasonably large or like k is less than equal n, that's it. That's the only constraint you have. Then what should be your algorithm? For this question only, it's still solvable. Then you need actually merge sort trees, which is kind of a similar idea to what I was saying before, that you can use segment tree-ish things. So it's actually like a segment tree-ish idea. But yeah, then you need merge sort tree. Yeah, I was thinking about this bit and you don't have anything simpler. Like ignore that for now. That is just a high level homework question. So, okay, we had this prime factors array, right? Now, what we want, what new things do we want? We want this A array, right? And we want this prefix array, which has this. Okay. And let's see the constraints of the problem. So you have t test cases and this thing goes till 1e5. Okay. Since this thing goes till 1e5, we can just put here 1e5. And no input taking is being done. Okay, now what someone recommended me, which actually I'll do, is make these less than, right? Now once these guys are less than, okay, you don't need those plus 5s anymore, and you have these things. Okay, cool. So now you take in t, and we get like these guys, and your output should be pretty simple. Prefix rk minus prefix l minus 1k, and instead of end, I'll prefer this thing because you're actually making a lot of prints, correct? Okay, so also So that's just fast IO. Okay, so this was the pre-calculation. Now we have to create array A and prefix array. That's the two things that we have to create here, right? Okay, so how will the array A look like? First, think about this. Someone said I have a spelling error. I don't know what the spelling error is. Oh, sorry. So you have this prefix I k equals prefix I minus 1 k, right? Plus AI equals k. That's it. And you're done. That's how your prefix array is created. Given you have the A array. Now, how will you create the A array? AI is equal to what? Okay, notice that A and B actually start from 2, so you don't need to consider whether 1 is considered a prime or not, whether 1 is a composite number. You don't actually care because they're always going to start from 2 and above. So you don't really care what A1 is. You don't care. So don't think about that detail. Otherwise, I was going to think about it. Yeah. So, okay, AI is actually going to be just prime factors I dot psi. This is pretty simple because notice what are prime factors. This vector was defined. This vector was actually like all the distinct prime factors, their powers, their value themselves, like 3 squares. So 3 is the first element of the pair and square, so 2 is the second element. And like all the distinct prime factors you have, all of them will come in this vector. So whatever the length of this vector is, that's how many distinct prime factors you have. So that's just AI. Okay, Mayank, I won't go through. It's just fast input output. I mean, I don't really know. I know what's the meaning of sync with stdio, but I don't really know the meaning of cn.diner. But I know that this thing is required to make it as fast as scanf printf. Yeah, you can even add cout diner, which is like to make the cout slightly faster. Yeah, I think this code should work right out of the box. Let's. Naveen, you probably won't care, but like it's the idea something like when you say sync with stdio false, you're basically saying sync with standard input output is equal to false, which means that cout and cn, like basically cn is not required to be in synchronously, like be in sync with scanf. So cn and scanf are both methods of taking an input, right? And they generally work synchronously. That means if you have some cns and some scanfs in the same code, then they won't read from one another. They'll work synchronously. But when you disable this flag, you basically say that don't work synchronously. So CNs stop waiting for scanfs. You can read it up on Stack Overflow or something. That's the broad idea, and that's why it becomes faster. Okay, so I just copied the input and like this is the output, which is correct. So let's just submit this. I mean, once you figure out the actual like the details of the question, it's pretty simple, like the implementation. So I mean, the key takeaway I would give here is that always have this like the fast method of actually being able to create. Oh, where's the word? Okay, I messed up. Okay, desktop, sorry. Yep, number theory. Yeah, so I mean, our implementation came out pretty quickly because we already had this prime factors method entirely with ourselves. So that's why this thing came out pretty quickly. Naveen, whenever you want to have fast IO, which basically means fast input, fast output, that's when you use this thing. Yeah, so we got it. Fast IO as in, okay, basically when you have a lot of input. I mean, that's the idea. Yeah, and here you have a lot of input because T is pretty big. T is almost 10 to the power 5, right? So you're actually taking in a lot of lines here. And also you're printing a lot of lines. And that's why we used \n instead of endl. Cool. So we got AC. So main thing here was to generally be thinking in this prime factors method, that just get the prime factorization quickly so that you can get something of this sort. And then in this specific question, creating the prefix sums was a simple task. So we just created them. And obviously, every time prefix sums recurrence always looks something like this. Prefix ik is equal to prefix I minus 1k plus something. Now you just have to fill that something correctly. Okay, so someone asked why is the prefix? Yeah, sure. So notice that we had this question, right? Given a range L to R, how many numbers does this range have value k in array A? Right? This was our question. Is this Rn not Rn? Well, is this Rn clear with this? That this was the question that we were trying to solve. If this is the question that we are trying to solve, then we can say, let's just get this thing from 1 to R and from 1 to L minus 1 and subtract the two values. It's equivalent. Like the answer of this thing is same as answer of this thing minus answer of this thing, which is basically saying get all the numbers in the range 1 to R which satisfy this property that we want, and get all the numbers in the range 1 to L minus 1 which satisfy this property that we want. And the property that we want is basically the numbers should hit the value k in the array, right? And getting this thing and getting this thing is basically both of them start from 1. That's why you get the hint that okay, it's a prefix thingy. So this thing is also a prefix and this thing is also a prefix. So how do I define these prefixes? That's how I define them. So I say prefix, what I want my prefix ik to store is, I want it to store how many numbers in the range 1 to I have value k. And because k is small, our second dimension is not going to be that big. We know that we only care about k less than equal 5. So our second dimension is going to be only at most size 5. And the recurrence that we use to create prefixes is this thing. That, okay, let's say you know prefix 9k equal 3. Now, calculating prefix 10k equal 3 is pretty simple, right? You can just say, use the prefix 9 guy, and then ask if A10 is 3. If A10 is indeed 3, if this is actually true, then you'll actually add a +1. Otherwise, you'll add a 0, right? Depending on what it is. If A10 is 3, then you'll add a +1 because you'll say, okay, the prefix 9 thingy, whatever we got, the answer from that thing, plus this new guy that we found at 10, which also hits. But if it's not a 3, then you just don't add anything. That's why we have this thing. So is that clear now? I hope this question is clear. I mean, yeah. If you still have any doubts, just go on chat. Or you can, like, if you think I went a bit fast, then you can even like go through the YouTube session later on. But like, I think we want to go fast because we're already up like 1.5 hours or something, 2 hours, and we still have one topic to go. I think we'll skip the next problem, which is CHMOD, and you guys can go through that problem. I'll just briefly explain the hack in that problem, the thing to look out for. Blah, 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 blah. Okay, notice the modulo can be anything in this question. The exploit is this thing. AI is pretty small. AI is just 100. So whenever you get a query, you will get 10 to the power 5 queries. In each query, even if you spend 100 operations, you can still get done. In each query, even if you spend 100 operations, you're still good to go. If you haven't read the question, just read the question later on. The main hint would be that AI is pretty small, so you can use this fact. And in each query, you can actually run 100 operations. And your modulo is not prime. So don't try to do some modulo inverse thingy. Don't try to do like 1 upon x under mod p, because your mod might not be prime. It might be a composite. So it becomes very tricky. Okay. So how many people do we have? Okay, we still have 40 participants. That's good. So we'll start with now the matrix thingy. We'll just discuss the theory. We won't discuss through the code. I mean, I can probably find some links later on for implementation of matrix expo, but we won't go through the. So you have this matrix expo thingy, right? So just so you know, a matrix is something like a 2D rows columns. Okay, this was a bad representation, more like 3, 5, 2, 7, 8, 4, 6, 5, 9, whatever. Okay. In this particular session, we are going to be discussing mainly square matrices, because luckily in comparative programming, you only care about square matrices a lot. You don't care about rectangular ones. So square matrix means that the length and the width are both the same. Okay. What's the motivation? The motivation is Fibonacci. So you have this recurrence, right? Fn is equal to Fn minus 1 plus Fn minus 2, right? And you have this F1 is equal to 1 and F2 is equal to 1, let's say, right? And you want to create new values. So how do you go about this? You say, okay, so our motivation is to calculate f of n fast. That is in order log n instead of on. So I mean, the slow method is just go through a for loop and like just keep on calculating fi. Say fi is equal to fi minus 1 plus fi minus 2 and blah blah blah, right? That's the slow method. We want it to be fast. So we say, okay, we want it to be something like log n-ish. Okay, how do we get that? So the idea comes from matrix expo. How? We'll define a matrix. So okay, right now I'll just give you the kind of like the entire idea, and I won't go like, first it might seem slightly magical, then later on you'll realize why it works. So you have this vector and you have this matrix A, and you have another vector. Okay. Now what I want is, I want a matrix A such that this vector is equal to A times this vector. Okay. Here vector means 2 entries. Something here, let's say 3, 5. This is a vector. Right? This is an example of a vector. So I want this vector, which is nth Fibonacci and n minus 1th Fibonacci, is equal to some matrix A times n minus 1th Fibonacci, n minus 2th Fibonacci. Now, what will this matrix be? Okay, first notice that the left side is 2 dimension, like the length is 2. So, and this thing is also 2, right? So what will be the dimensions of your matrix? Your dimensions of the matrix will be 2 by 2, because I mean, these are 2 guys. So definitely this thing needs to be 2, right? And also you want to create 2 such values. So this thing also needs to be 2. Now, how will you actually create these values? So let's think about these values as A, B, C, D. You don't know those values. I mean, somebody in the comments actually put those values, but like for generic recurrences, I mean, for Fibonacci, you can memorize the values if you want to, but let's say I change the recurrence slightly. I change it to say something like this. Now this is no longer Fibonacci. You should still be able to create those values if you want to, right? A, B, C, D. So you need to know the method, and like memorizing over the long term won't help you. So here you have Fn, here you have Fn minus 1, here you have Fn minus 1, here you have Fn minus 2. Now notice this thing needs to be multiplied with this thing. That means, and Fn is going to be this thing. That's how matrix multiplication works. I'm not sure if everyone knows what are matrix multiplication, but that's how matrix multiplication works. Basically, this value going to be multiplied with this value, plus this value going to be multiplied with this value. So basically, Fn, which is this value, is equal to A times Fn minus 1 plus B times Fn minus 2. Similarly, Fn minus 1 is C times Fn minus 1 plus D times Fn minus 2, right? Now just plug in the values of A and B that seem most reasonable to you. Okay, Neil is asking matrix multiplication. Yeah, sorry. So matrix multiplication is generally this way. I'll just explain for matrix into vector, because in our case, we only care about a vector, right? So let's say this is a vector. So what we'll do is we'll dot product this row with this column, then we'll dot product this row with this column, and so on. Example, let's say this row is R1, this row is R2, so on, and this column is sieve. Then the multiplication is going to look like R1 dot C, R2 dot C, so on. Here, R1 dot C, what I mean by dot is basically saying this row multiplied by this column, right? This is R row and this is C1 column, which means the first entry multiplied by the first entry. So let's say this first entry is, I don't know, let's say these are A, B, C, and these are D, E, F. Then A times D, which is first entry times first entry, plus second entry times second entry, B times E, plus third entry times third entry, which is C times F. That's it. That's the row. That's the dot product. So R1 dot product column. So when you're doing this multiplication, you're saying this thing dot with this thing dot with this thing are going to be the different values. So this value is going to be R1 dot C1. This value is going to be R2 dot C2, C, and so on. Does everyone get the broad idea of matrix multiplication? You're basically saying, at least when you're multiplying with vector, you're saying this thing multiplied with this thing, then this thing multiplied with this thing, so on. And when I say multiplication of two things, I'm actually referring to the dot product, which I explained here, which is basically taking first entries, multiplying them, second entries, multiplying them, third entries, multiplying them, so on, and adding all those entries. So here in the Fibonacci, you got this thing, right? A, B, and CD. Now think about this. Okay, first look at this CD. This is pretty trivial. You can say, oh, Fn is here, Fn is here. Just put this C as 1 and put this D as 0. And this equation is satisfied, right? Trivially, it's satisfied. And what about this thing? Here, you want to create Fn using Fn minus 1 and Fn minus 2. How will you create it? You'll say A should be 1, B should be 1. Why? Because that's how you define Fn. You defined Fn as, like, you defined Fibonacci's as like the sum of the previous two guys. So you got A1, B1, C1, D0. So Fn minus 1, this vector is equal to 1, 1, 1, 0 times Fn minus 1, Fn minus 2. Now try this out. Let's say you know F1 is equal to 1 and F0 is equal to 1. Let's say. So you have this thing here, 1, 1, and you have 1, 1, 1, 0. Just try the matrix multiplication of this thing. It comes out to be 2, 1, right? Which is equal to F2, F1. Not a surprise, right? And let's try this again. Let's say you have 2, 1 here, and you again multiply with this thing, 1, 1, 1, 0. What does it come out to be? 3, 2, which is F3, F2. Not a surprise. Then let's try again. 3, 2, 1, 1, 1, 0. Right now, we haven't actually improved the speed. We are just showing that you can do matrix multiplications to create next Fibonacci's. So this thing comes out to be 5, 3, which is actually F4, F3. Again, expected, right? So you can just, I'm just doing a sanity check to actually show you that this thing is true. It's not like, it's not incorrect. It's actually true. And we actually showed this, right? Now notice. So, okay, let's represent this matrix as A again for simplicity. So we got this thing, Fn minus 1 is equal to A times Fn minus 1, Fn minus 2, right? You can rewrite this thing as A times Fn minus 2, Fn minus 3, right? This entire term can be written as this thing, because just use this recurrence again. Like this thing can be again expanded into A times Fn minus 2 and Fn minus 3. This matrix times this vector. So this entire thing can be represented as Fn minus 1 can be represented as A times this thing, which is A times Fn minus 2, Fn minus 3. And you have two A's together, so it's A square actually. And Fn minus 2, Fn minus 3. Now notice you can keep on doing this. Again, try to represent Fn minus 2, Fn minus 3 as A times Fn minus 3, Fn minus 4. and so on, right? So the idea is that this thing will come out to be a to the n. This thing will come out to be f1. This thing will come out to be f0. Like after a few steps, you can keep on expanding this thing as a times the previous guy, and then again this thing as a times the previous guy, so on, right? Now an important thing here is, what does a to the n actually means? Like I did a square here, I didn't explain what a square is. So when you are multiplying two square matrices, let's say a b c d e f g h, the multiplication actually looks like this: ab into eg, this is the first cell, then AB into FH is the second cell, then CD into EG is the third cell, then CD into FH is the fourth cell. Right. So, I mean, I won't explain matrix multiplication. If someone is completely new to this, it's very hard to pick it up instantly right now. I would recommend just Google this up or like look up math NCERT or something. Right. Yeah. If you forgot how matrix multiplication works, but that's the idea. You basically multiply the rows here with the columns here to get different values. Each value is a dot product of a some row and some column, right? So you have a to the n here, and you have this thing. Now the question is, okay, once you can calculate a to the n, which is basically some 4 values, if you can calculate these 4 values, then multiplying it with this thing is pretty simple, right? So if you have a n somehow by magic, then calculating fn is fast, because a to the n is basically a 2 cross 2 matrix, and f1 f0 is a 1 cross 2 vector, sorry, 2 cross 1 vector, and multiplying these two things is order 1. You can just like, if you already know what a to the power n is, then you can just plug it in here. You have this, just do the multiplication and get this and this, but you can ignore this value. You don't need this. You just get fn. So so can we use Strassen method? Okay, Ahona Strassen is actually used when you have big matrices. Like, okay, so the complexity of multiplying like a square is actually order k cube, where k is the size of matrix. Right? I mean, I'm not going to go in depth why it's k cube, but that's the trivial method. But I mean, using Strassen, you can probably get something like k to the 2.7 or something, but you don't really need, because in this question k is 2. So even 2 cube is not slow. 2 cube is just order 8, which you don't really like, which doesn't really impact you. Okay, so this is our feedback form, which we would recommend everyone to fill in. Like, I'll still go through this. It's just that in case you're leaving in between or something, just fill in this feedback form before you. So, okay, that's why you don't really care about Strassen multiplication, because k is so small. It's like just 2 or 3 or something, that doing Strassen or doing normal multiplication, it's negligible. The difference is negligible, because 2 cube versus 2 to the 2.7 is nothing. It's order 8 versus order 4. You don't care. So our question reduced to finding a to the n. If you can find a to the n fast, then you're done. And you know already that a is 1110. Now you need to find a to the n fast. That is in order k cube log n. Here k is again 2, which is basically means order log n, because again, just put in 2 to the cube is pretty small, just ignore it. So 8 log n, which is log n. That's how fast I want it to be. I don't know right now what's the method. Okay, first think about the slow method. So the slow method is going to be, just take a, keep on multiplying it with itself. Right? Keep on multiplying it with itself, and it'll be slow. How slow it will be? You do n multiplications, and each multiplication is k cube. So you do order k cube n, fine. And k is pretty small, so ignore it. So order n. But this is the slow method. Just multiply the matrices naively. What's the fast method? Now, I'm not sure if every one of you has gone through binary exponentiation. The idea is this. if you're trying to calculate, let's say a to the 20, then it is same as saying you're trying to calculate a to whole to the 10, which is same as saying you're trying to calculate a square whole square to the 5, which is same as saying you're trying to calculate a square whole square times that. Okay, it becomes uglier as I keep on doing this, but like, yeah, I'll write it in a more cleaner way. A to the n is equal to a square to the power n by 2 if n is even. A times a to the n minus 1 is odd. Let me explain this. So example, if n is 10, then what I'm saying is a to the 10 is equal to a2 whole to the 5. And example, if n is 9, then what I'm saying is a to the 9 is equal to a times a to the 8. Now, again, if you start thinking of a square as b, then again you can say what is b to the power 5? B to the power 5, according to this logic, is b times b to the 4. And similarly here, a times a to the 8. Now what is a to the 8? You can again apply this logic that a to the 8 is basically a square times whole to the 4. That's what a to the 8 is. And again, a square can be written as b or like c, basically some other variable. And you can keep on doing this, right? So basically, a to the n is equal to either, okay, the idea is this. You can either half the exponent. So let's say previously the exponent n was 10. Now you halved the exponent to 5. Next time, since the exponent is odd, you'll decrement it by 1. So it will become 4. Now it's again even, so you'll halve it. So it will become 2. Again even, so you'll halve it, it will become 1. And for obviously, for a to the 1, it's just a. So just return a. And you're done. Right? So that's the idea. That a to the n can be solved in log n. Okay, think about this. Now I showed you for n equal 10 that it drops to 1 pretty fast. Think about a generic n. If you have n, in the next iteration, it will probably become n by 2. In the next iteration, it will become n by 4, and so on. This will happen if it's even always, right? But it might become odd, you'll say. It might become odd in between. But it won't become odd a lot of times. Let's say n is 100. Then, okay, basically, whenever it becomes odd, in the next step, it will become even, right? Because when it's odd, this is even. So if this is odd, then this is even. And when this is even by 2, right? So in consecutive 2 steps, if you have, let's say this is the function, f of n is equal to n by 2 or n minus 1, if n is even, and if n is odd, right? I'm just trying to show you that doing this recursively is pretty fast, that you can actually drop this exponent pretty fast, pretty quickly. So the idea being that if you have this thing, and then f of n is definitely going to be less than n by 2. This is going to be 2. Think about it. If n is even, then f of n is going to be n by 2, right? And f of n is also going to be less than equal n by 2. You don't care whether n by 2 is even or odd. This thing is definitely going to be smaller. And if n is odd, then f of n is going to be n minus 1, which is even because n was odd. So n minus 1 is even. So f of n is going to be f of this thing. And since we know that this is even, it's going to be n minus 1 by 2, which is less than n by 2. So basically, after every 2 steps, you would have dropped your exponent by at least 2, by at least half. Like you would have halved your exponent. Let's say originally the exponent was 100. After 2 steps, like let's say this is some step here, some step here. After 2 steps, the exponent is definitely going to be less than equal 50. Then again, after 2 steps, the exponent is again going to be definitely less than equal 25, and so on. So how many times can you take this double jump, like these two steps? You can only take this double jump log n times, because after log n times, the thing will just be vanish. Like 100 will just become 1. And like, and in each time, how many steps were you taking? You were taking a double jump, so 2. So in order to log n, you can calculate a to the n. Okay, I ignored here that you can calculate a square pretty fast. Calculating a square is just order k cube operations. And in our case, it's a 2 by 2 matrix, right? It's a 2 by 2 matrix. So k is equal to 2, which implies order k cube is equal to just 8. So it just takes 8 operations to actually calculate this thing, even though the numbers themselves might be pretty big. And similarly here, when this is a matrix and this is a matrix, both of them are 2 cross 2 matrix. So the multiplication within them is also again 8 operations. So it's also cheap. Yes, matrix multiplication is not similar to normal multiplication. I mean, there are some differences, but the same property that you have is that it's still cheap when the matrix is small. Okay, Devansh asks, why do we always take 2? What do you mean by 2? As in, okay, log base 2. Oh, interesting question. Okay, think about this thing. You can even write this recurrences like this. This is interesting question. Good question. Okay. Instead of 2, if you want to write, you can write like this. If n mod 3 is 0, if n mod 3 is 1, if n mod 3 is 2. Like if we take 4, but Devan gave you gave 4 as an example, I just gave you 3. The issue that comes here is that if you start using this recurrence to solve a to the power n quickly, the issue that will come is, notice in this case you are doing 3 multiplications, right? You're doing 3 multiplications. In this case you are doing 1 multiplication, so 2 multiplications. In this case, okay, I wrote this pretty bad. Yeah, so it's a to the n minus 2. You're doing 2 multiplications and 1 multiplication, so 3 multiplications, right? On average, you're doing 3-ish multiplications. The issue will be each time you're doing 3 multiplications and you're dropping the problem by a third. The complexity, like you can try to calculate the complexity. I can bet you it will come out to be 3 log n base 3. Earlier, it was 2 log n base 2. Right? When we picked this thing as like 2-ish everywhere, it was 2 log n base 2. Now it's 3 log n base 3. And this is worse. The comparison is simple. Pick 3 log n base 3 here, 2 log n base 2 here. Now you need to know some logarithm properties. Example, this thing is going to be written as log n base 2 upon log 3 base 2. This thing can be written as this thing. It's the same. So this thing is this thing versus 2 log n base 2. Okay. Now these two cancel. And this thing goes here. This thing goes here. So you have 1.5 on the left side. You have log 3 base 2 on the right side. Right? And you can just calculate log 3 base 2 is going to be pretty small. It's 1.5, so it's actually bigger. Okay, maybe I missed something. I'm not sure. Yeah, I'm not sure. I think this should be more expensive, but I'm not sure. It might be cheaper. Should not take 2 LHS. Yeah, maybe I did some arithmetic error. I'll rectify this and like put it on the blog post maybe as an update. okay, let's ignore this part. Like the important thing is, let's say you have some other recurrence. I'll just show you an example of how to solve generic recurrences. Let's say you had this recurrence, right? I'll just give this as a last example and then we can wind up. So let's say this was the recurrence, which is Fn is equal to Fn minus 1 plus 2 times Fn minus 2 plus 5, some random constant. How do you do this? You'll say Fn minus 1 come on the left side. Okay, notice I am always putting two guys on the left side, but they can, okay, let's actually make this example slightly harder. Plus Fn minus 3 plus 5. Now you'll actually need three guys on the left side. Fn minus 1, Fn minus 2. Then you'll need your magic matrix, and then Fn minus 1, Fn minus 2, Fn minus 3. Now, what will be the first value of the matrix? Notice Fn is what? It's the combination of these three guys, right? So it's going to be what? It's going to be 1, 2, 1. But we also need a 5, right? Notice we also need a 5. So this is actually incorrect. You actually need another dimension. Which is 1. I'm going through this pretty fast, but like, yeah, just try to get the hang of this. So Fn is equal to 1 times Fn minus 1, so 1, 2 times Fn minus 2, 2, 1 times Fn minus 3, so 1, and 5 times 1, so 5. Notice this times this is actually giving you Fn, which is correct. The next thing, Fn minus 1 is going to be 1, 0, 0, 0, because 1 times Fn minus 1 plus 0, 0, 0, 0. Then Fn minus 2 is going to be 0, 1, 0, 0, because Fn minus 2 is just 0 times this thing plus 1 times this thing plus 0 times 0 times blah blah blah. Basically just keep this term and ignore all the other terms. What is 1 now? 1 is going to be 0, 0, 0, 1. Basically 0 times this thing, 0 times this thing, 0 times this thing, 1 times this thing. Okay, Neil asked, can't we just ignore 5 and later add 5? Yes, you can. It doesn't work always. Okay, for this particular question, you can. Yeah, you're correct. Let's just add 5 later on. Ignore it. Oh, no, you can't actually, right? You can't. Yeah, you can't. Because think about this. If you ignore the 5, like you'll probably miscalculate the smaller values. Let's say F3 is going to be 20, but you will calculate it as 15 because you ignored the 5. So your calculation for F4 will also be messed up because instead of picking 20, you'll actually pick 15 inside. Like you miscalculate everything by a plus 5. You'll have this plus 5 error everywhere. So even these guys will have the plus 5 error, right? And so it will compound. Yeah, Anishwar has a good idea that add 5 to the end. Maybe that might work. I'm not sure. But like this is the most simplest method if you don't want to get into the technical detail of how to solve it. But so you can even do this thing. Other kinds of recurrences like Fn is equal to Fn minus 1 plus 3 times n plus 2 n times, I don't know, n times 4 to the n. Even these can be solved. They're trickier to solve, but they can be solved. I won't go through them, but like just so you know, this thing can also be solved. Other example, okay, one interesting thing I'll show you. Let's say you want to keep Sn also, which is basically F1 plus F2 plus dot 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 up till Fn, which is basically sum of all the terms up till nth one. This thing can be calculated also. How? Just keep Fn, Fn minus 1 and Sn. Keep all these three guys. I'm just going to show it for Fibonacci. So basically the S terms is basically the sum of those guys, right? You can even keep this guys. So Fn is basically what? Fn minus 1 plus Fn minus 2, right? So 1, 1, 0, because this thing doesn't contribute. What is Fn minus 1? Fn minus 1 is just this guy. And this guy is this guy. What is Sn? Notice this thing, this thing, this thing. Yeah. So Sn is basically saying add Sn minus 1, basically all the previous terms that you got, all the sum of all the previous term, and plus Fn. And what is Fn? Fn is just 1 times this and 1 times this. So that's why 1 times this and 1 times this. So if you use this matrix, then the last column, last value will actually give you Sn, which is actually F1 plus F2 dot up till Fn. So you can even get prefix sums this way of your recurrence, like the sum of the first n Fibonacci's or the sum of the first n these guys, Fibonacci's or whatever, like the random recurrences. Yeah, so that's like the super fast tutorial on Matrix Expo. I mean, you guys should definitely read some blogs. I'll try to share them up on the blog post, some better blogs on Matrix Expo, because I think I went slightly fast and I couldn't show you examples like this one, which is a pretty good example. And like, this is one of the tricks. Another trick that I know of is that if you have this thing like a plus a square plus a cube dot up till a to the n. Let's say you have a as a matrix and you want to calculate this thing. For some reason, you want to calculate this thing. You can't do GP formula. In normal maths, you have a plus a square plus dot up to a to the n. You do this GP formula, which is something like this: a to the n plus 1 minus a to the n upon a minus 1, something like this, right? In Matrix Expo, this becomes pretty hard because you get this thing and you don't know what this means actually, because A minus identity matrix, but you are taking the inverse of that matrix. Taking inverse of matrix is pretty hard. So actually calculating things like this for matrices is hard, but for numbers it's easy. And there are questions actually which actually ask you to calculate this thing. So yeah, that's also another interesting thing. I'll try to share links for these, as many as I can find. That's pretty much the end. In which type of problems we use Matrix Expo beside Fibonacci? Okay, good question, Devansh. So mainly questions of DP which have huge n, huge, like n will be something like 10 to the 12 maybe, because then order n is generally not doable, right? Obviously. And then you actually need something like order log n times k cube, where k is the size of your matrix, which is generally going to be less than equal 50, or like in this case it was 2 for Fibonacci, but in general it's going to be less than equal 50 for most cases. Your k, so that this thing actually is not that big, and your log n will be there. So for DP questions which have pretty huge values and which are counting questions. So there are two types of DP questions. One are counting questions, which are more mathy, and the second ones are maximize/minimize questions, which is basically trying to maximize or minimize something, some kind of function. When you're doing maximize or minimize questions, you can generally not apply Matrix Expo. Matrix Expo only works for counting questions. How to use modulus with this? Okay, good question. When you have this matrix, like let's say A, B, C, D, and you have this vector E, F, when you're doing the multiplication, just do it under modulo. So let me show you. A, B, C, D, and this was E, F. You're doing the multiplication. What's the first value? The first value is AE plus BF, right? Just do this under modulo P. And the second value is CE plus DF. Just do this under modulo P. Keep all the things under modulo P. Every addition, every multiplication should be under the modulo. And that's how you just introduce the modulo inside your entire matrix multiplication. Everything will be under the modulo. Yeah, Devansh, it's a bit difficult. I mean, it's a slightly advanced topic. I won't say it's a trivial topic. Like even covering it in the DSA series was it's a hard topic, and it's not that useful also. I mean, okay, it is very useful in comparative, but it only starts coming up in intermediate questions. It generally never comes up in like easy or beginner or easy medium questions. It'll only start coming up in like medium or medium hard questions. But like, I would try to share links regarding Matrix Expo. Yeah, because I can understand that through a half an hour or 45-minute session, it's not enough to get all the details correct. Human div 1. Yes, more or less. Yeah. I don't know exactly how CodeChef div 1 works, but yeah, I won't say in a contest of say 5 problems, definitely a Matrix Expo question won't be the first 2 problems. it'll definitely be the third or the fourth problem. Yeah. All right, so that's pretty much it. Where you share link? Oh, I haven't shared them yet because I'll have to find them, but I'll share them on the CodeChef discuss. Yeah, the place there where I shared this, the live DSA. Yeah, so I'll put in here as an update. Like this is update 1. I'll just put it in as another update. Yeah. So you're welcome, guys. Can you give advice on how to master DP? Oh, Devansh, we had this. I don't know if you've seen this, but like, I think our general advice for DP was, in fast competition, we encounter recurrence questions, just question 1 or 2, or else something else more easier. If the question is the first or the second question, then generally probably something similar exists. Yeah, if it's the first or the second question of the problem. Like if a lot of teams have solved it, then you probably don't need to go to matrix expo. You can probably math it out and it'll come out to be like something like 3 to the n plus something. Yeah, like some simple recurrence. Like let's say I create a recurrence saying Fn is equal to 2 times Fn minus 1. Then Fn is just 2 to the power n, right? So sometimes you have like some simple recurrence which they actually try to hide. Like, yeah. Yeah, Devan. So this was our clue basically, that like the advice for DP, our main advice for DP was that you should try to solve as many questions as you can by yourself. So don't try to go through a lot of DP questions on Geeks for Geeks. I wouldn't recommend that. I would say just go through like maybe 7 or 10 classical questions so that you know what all states are possible in DPs and what all transitions are possible. But don't try to go through a lot of questions. What you want to do is maybe just look at like 7 to 10 solutions, and then try out questions on your own pace. Maybe you do only 30 questions, but try to do them yourself. Like after having seen the classical 8-10 questions, whenever you pick a question, try to give it a lot of time, maybe 1 hour, maybe 2 hours, and try to come up with the recurrence yourself instead of Googling it or instead of reading up on the internet. The benefit that comes is that after like doing 30-40 questions of this sort, you'll probably be so good at this that during a contest, when you see a question, you won't be worried that have I seen this question before or not. Because in DP, when you are in a contest, generally the recurrence won't be repeated. I mean, for classical DPs, longest increasing subsequence, or classical DPs, the recurrence is pretty known to everyone, so they are repeated. But in actual contests like ICPC regionals or something, you'll never find a problem having the same recurrence as another problem. So it's very important that that stage that you can actually form the recurrence yourself during the contest time. And I feel it's like you acquire that skill more if you spend time more thinking about how to solve DPs rather than reading a lot of solutions. So maybe just read 8 to 10 solutions of the classical ones so that you have enough ideas, you know how all recurrences work. Maybe, yeah, maybe you can shift to Codeforces or CodeChef, or even if you want to do Geeks for Geeks, you can do Geeks for Geeks, but just keep in mind that you don't want to look at the solutions. I mean, just think about the problem enough and like maybe code it on their practice or whatever. They have a practice section, I know. And then once you're confident that your solution is correct, then maybe look at the solution just to confirm that, okay, was it correct or not? Or maybe implement it on the practice section, get an AC. So I'm just doing this like for 2 minutes. I'll just end this session after this. Shall we practice Euler project questions or more famous website? I won't recommend it, Aaron, because I mean, project Euler is actually quite different from competitive. It's slightly different. Like if you just do the first 25-50 questions, you probably won't gain that much in terms of math. If you start doing like, I think 100th question or two up, like after 50th question onwards, then I think the difficulty actually increases and it might be helpful for Codeforces or CodeChef. But before that, I honestly don't think it will be that helpful. I know there is HackerRank ad infinitum. There's a contest ad infinitum, something like that. And it's a math contest. It used to happen. I don't know if it still happens, but it used to happen at least like a year or 2 years back. It used to be a weekly contest of some sort or a monthly contest, like once a month. And all the 5 problems used to be math problems. But they still have had competitive programming ideas in it. So I think that's a pretty good place to practice math questions specifically if you want to. I think Neil just practice on CodeChef or Codeforces. Yeah. I honestly don't believe that courses will help a lot. Yeah. Cool. How much time do I ideally divide between practice and exploring new concepts? I feel just like, I mean, if you're practicing and you find like you're so stuck at a certain question and then you see the editorial and then the editorial says that, oh, this is a new concept, then you read that new concept. And like, once you've read that new concept, you maybe try out 8 to 10 questions from Spoj or like some websites to just get a hang of that concept, or like what are the most classical questions based on that concept. Yeah, like everyone varies in these kinds of things, so I don't have a generic advice for everyone. Yeah, anyway, thanks guys, and sorry it was a long session. I would say upsolving. Upsolving is generally more preferred. I mean, people are lazy for upsolving, but upsolving actually generally improves your level that rather than solving fast competitions. Because in competition, let's say there are 7 problems or 6 problems, you'll probably end up doing 2 or 3 maybe. Like even I, like maybe you'll end up doing 3 or maybe 4, whatever your current level is. But the idea is you won't have enough time to actually try out the hard question. The hard question here I mean is the question that you feel hard. Like let's say you're able to do in a Codeforces Div2 contest, you're able to do Div2A, Div2B, Div2C, but you're not able to Div2, Div2D. In a timed environment, it's very hard to get the Div2D under 40 minutes or something. So upsolving is important because during upsolving, you'll take 2 hours to solve that Div2D. And once you've solved plenty of Div2Ds, then you'll actually have a good shot at solving a Div2D during the contest. It's super rare to have known people who just gave contests and were somehow able to solve Div2D after some time. Like let's say for the first 6 months that guy wasn't able to solve Div2Ds, but after 6 months that guy was able to solve Div2Ds, but he did not upsolve anything. I haven't seen a case like that. I haven't heard of people actually being able to do that because they didn't give Div2Ds enough time. All right, so we should end the session. Yeah, it's getting pretty late. Cool.